Dear learners, let us look at the refraction of water waves. Let's start by looking at the objectives of this lesson. First of all, you should be able to describe what is the refraction of water waves. And then secondly, demonstrate the use of water waves to show refraction due to change in speed. So as we have said before, that we are using a ripple tank to study water waves. So we are also going to use the ripple tank even in this case where we are studying refraction of water waves. What we do here, we pour a small amount of water on the tray of the ripple tank. A glass is then placed inside the tray so to give two regions. One region is going to be deeper and the other one is going to be shallower. The shallower region being the one over the glass. So here, this is just a ripple tank. This we only show the part, the tray, the water in the tray. So in that part, we put a small glass. So here is this glass. So this is the glass that we put inside the tray, so that it gives two regions. Remember that there was water inside the tray. And then when we put the glass, so this region is going to be deeper than the region over the glass, because now the glass kind of increases the size of the base, so that the water above the glass is shallower than the water in the other region. So this region is deeper and the region over the glass is shallower. The glass is placed such that its edge is at an angle to the upcoming wave fronts. So let me just remove everything here. So here are the upcoming wave fronts. So we put the glass so that it is at an angle to these upcoming wave fronts. As you can see, it is at an angle. Because if we have the upcoming wave front like this, then we put the glass to be like this, there won't be any, the change won't be easily to see, but there is going to be some change in the behavior of the waves over the glass. Straight waves are generated by vibrating the bar. So we remember that there is a bar in a ripple tank which is connected to a motor that when it vibrates, it causes waves to form. Then the behavior of the waves is going to be studied by viewing the image of the waves on the screen. So you remember that there's going to be a screen below the tray. When waves enter a different medium, they are going to change speed. The speed of the wave change. So here, when we talk of a medium, we are referring to two regions. So here we have this region, which is the deeper region, the region where there is no glass, and then this region is the shallower region. This one is shallower. This is the shallow region. So we have two regions. So you remember that when waves enter a different medium, so here in this case we are referring to the shallow and deeper regions. So the speed is going to change. So it is going to depend whether it is coming from deep region to shallow region. Like in this case, the waves are coming from deep region and then they are entering a shallow region, which is they are entering now this region, which is they are entering a different region now. All right. So this effect is called refraction. So when we talk about refraction, it is when waves change their speed upon entering a different medium. And it has got two other effects. First of all, one, the wavelength of the waves can increase or decrease. Secondly, the wave can change its direction. So we are going to look at when does it increase, when does it decrease. So if the waves slow down, the waves will bunch together, causing the wavelength to decrease. When does the wavelength decrease? That is when the wave speed has been reduced also, or when the wave slows down. That causes the wavelength to be smaller. The waves will also start to travel closer to the normal. In other words, when we say they travel closer to the normal, we mean they are going, the ray is going to bend toward the normal. If the waves speed up, they will, so here it's speeding up, then the waves are going, they will spread out, meaning the wavelength is increasing. So meaning the wavelength increases. The waves will also turn slightly away from the normal. So let us look at this animation that is shown here. So here we have this region, which is the region of deep water, and this region, it is the region of shallow water. So here are waves that are coming this direction. So these are the waves that are coming, so I'm going to draw the arrow to show the direction of the waves. So you observe that upon entering the shallow region, so this is the barrier from that divides the shallow and the deep region. So upon entering the shallow region, you can see that the waves now are going to, the speed of the wave is reduced. And also you should see that the wavelengths are small in this part. They are smaller here than in this region. So the wavelength is the distance between two wave fronts. So let's take those white air regions as the wave fronts. So if we measure the distance in the deeper the wavelength on in the deeper region, we find that it is greater than the wavelength in the shallow region. So that's number 2. We said the speed decreased. Secondly, the wavelength is reduced. Speed is also reduced, and they bend towards the normal. So if we were to draw a normal here, so let me draw a normal, so let me use a different color to draw a normal. So if we were to draw a normal here, so this is the normal. All right, so you can tell that if, let's draw another, the refracted waves. So you see now, remember that the ray, which is the arrow, has to be perpendicular to the waves. So you can see now that the arrow, it didn't continue straight like this. But what happened, it has to bend this way. It had to bend this way. And it is bending towards the normal. So that this angle I, which is the angle of refraction, angle of incidence, is greater than R. So this one is R. So here I is greater than R in this case. So this is a simplified diagram of what happens. The shallower water, I mean the wavelength here has been reduced. You can see here the wavelength has been reduced in this part. So if you could measure the distance between two wavefronts in this region, you find that it is smaller than the wavefront here. So the reason speed decreases is because, speed is affected by wavelength and frequency. So here the frequency has not changed because the frequency is determined by the motor. So the frequency doesn't change. But if the frequency has changed, so the wavelength has changed, has reduced, it means the speed is also going to reduce. From deep water to shallow water. So this is an example. When the incident wave front entered the shallow water, these are the things that happen. The direction of their travel bends towards the normal. So that's number 1. Number 2, wavelength decrease, which is the distance between two wavefronts, is going to decrease. And then frequency remains the same. As we have said, speed decreases. So you should be able to tell this. So here is what happens. So here, this is another example. So this is a shallow region. this is a shallow region and this is a deep region. So I think this one has to be opposite. So this one has to be deep and this one has to be shallow. So I think this one was this is incorrect. So that's what happens. The rays decrease. I mean the what to call, the waves bend toward the normal upon entering the shallow region. What happens when now it is moving from shallower regions to a deeper region? When the incident wavefront enters the deep water, the direction of their travel bends away from the normal, and then the wavelength now increases, the frequency remains the same, and the speed increases. Okay, so here you can see this one is a shallow water and here is a deep water. You can see the wavelengths here in the deep water are smaller than the wavelength in the shallow water. Okay, so what happens here is that it is going to bend away from the normal. So if you could see here, if you, this is the angle, this angle is the angle of incidence, and this angle is the angle of refraction. And you can see that in this case, I is less than R, while in the other case, I was greater than R. So here is I, here is R. So this is a simplified diagram showing refraction from shallow water to deep water. All right, so here let's look at these example questions. Some plane waves travel on a surface of water in a tank. They pass from a region of deep water into a region of shallow water. Figure 6.1 shows what the waves look like from above. So remember in the beginning of this lesson I said we put the glass that forms the shallow region so that it is at its boundary or its edge is at an angle to the upcoming waves. But in this case, it is parallel. What happens here? So this is deep water, this region, and this is shallow water. So it means in this, where there is shallow water, then there is a glass. If it was a ripple tank, there is a glass, but in this case, it's just a tank. But if it was a ripple tank, we would say there is a glass over below in the region of the shallow water. So let's look at the question. State what happens at the boundary, if anything, to 1, the frequency of the waves. What happens as the wave enter the shallow water? What happens to the frequency? There is nothing, so it remains the same. So that would be the answer here, remains the same. It doesn't change. Why does it change? Why? So here we were not asked to explain. We were just asked to state what happens. But we could explain that it doesn't change because frequency is determined by the motor. So the motor is still generating waves at the same rate. So the same equal number of electrons, I'm very sorry, equal number of waves generated per second. And then the speed of the wave. What happens to the speed of the wave? So the speed of the wave is going to decrease because now it has entered a shallow region. The wavelength also decreases because it has entered a shallow region. Why does it decrease? Because if the wavelength, you can see here, the wavelength in the shallower region is smaller than the wavelength in the deeper region. If you could measure the distances between two wavefronts, you could just tell that. Even without measuring, it's just easy to tell from the diagram. Okay, so speed is equals to frequency times wavelength. Speed is equals to frequency times wavelength. What is this? Frequency times wavelength. So if the frequency didn't change, but the wavelength has changed and it has decreased, it means V is also going to decrease. The wave has a speed of 0.12 meters per second in the deep water. Wave crests are 0.08 meters apart in the deep water. So what does this tell us? So this tells us the frequency, the wavelength. So this is the wavelength, 0.08 meters. So this is the wavelength, which is 8 centimeters apart in the deep water. Calculate the frequency of the source producing the wave. State the equation that we have used. So we know that speed is equals to frequency times wavelength. So we want to calculate frequency. So frequency equals to speed over wavelength. Equals to speed over wavelength. So now, if we calculate here, what are we going to get? So speed is equals to 0.12 over the wavelength. What is the wavelength in this case? It is 0.08. And then we calculate this one. Okay, so let me use my calculator. 0.12 divided by 0.08. We're going to get 1.5. So that is the frequency, 1.5 hertz is the frequency here. So you get 3 marks just by writing that. Figure 6.2 shows identical waves moving towards the boundary at an angle. On this figure, draw carefully the remainder of the waves A and B plus 2 previous waves which reached the shallow water. You will need to use your ruler to do this. So we need to draw the waves. So what happens here is that it is entering shallow water and it is going to bend towards the normal. So that if we have this is the wavelength, here it is going to do what? It's going to bend towards the normal. So something like this. Because because if we were having a normal here, so let's draw a normal here. So now the wave doesn't continue straight, but it does what? It bends towards the normal. So that's what is going to happen. So the wave fronts this side are going to be taking this direction. So here, how can we continue the remaining part of A and B? So let's just go back to this part. So you see, sorry for that. You see, this is the reaches. So this was deep water. So the remaining parts they want us to draw is this part for like these 3 waves, like this 3 wavefronts. So you see how it bends. So let's continue. Let's draw it even this side. How are they going to appear? So this, unfortunately, I don't have a ruler to draw these ones, so that they are parallel to this. So we're asked to draw 2. So yeah, so you unfortunately I'm unable to draw it very well here on this screen. Yeah, but however it has to be parallel to this, and because it's entering shallow water, it means they are going to be closer to each other than in the previous diagram. So something like this. And here these ones come here. Just let me just start afresh. These ones I'm completing A, I'm completing B. Oh yeah, let me complete B. Yeah, my B is, so it has to bend. I'm trying to draw it so that it appears like it has bent, And then now I have to use a smaller. Is it small? Yeah. I hope you, ladies and gentlemen, can see. So just draw the, it will be something like this. So just draw the what? The wavelengths in the shallow region to be smaller. Mine are not very clear because it's very difficult to draw here. So here is another question. Figure 5.1 shows a view from above of water on the surface of the water in a tank, in a water tank. The wavelength, the wavefront A, B is traveling in a region P. So region P is this. So this is region P. It's traveling region P towards region Q. So this is the direction. So it is moving towards the region Q, where the water is shallower and the waves travel more slowly. So just like you can see how the waves are now traveling, they are traveling slow in region Q. So now we will need to find out which one is correct here. Oh, maybe let's read the question. So sometime later, the wavefront has moved into region Q. C, D, C, E, C, F are suggested position of the new wavefront. State which is correct position of the new wavefront. Sorry for that again. So want to state which is the correct region. Is it C, D, C, E, C, F? Okay. So now here, let's look at A and B. So here what is happening is that A has reached the shallow region. Sorry, this part B has reached the shallow region. And what is going to happen is that it is going to start traveling slower than A. So the distance traveled now by B is going to be shorter than the distance traveled by A. So now this is the distance. So we can take this one and this one. So you can see that the correct one then is going to be CT because B traveled to D and it is shorter than the distance from A to C. So our correct answer is CD. Alright, sorry for that. Let's continue. Explain your answer to this one. Why did we choose CD? So let's go back to the diagram. Okay, let me remove these things. Why did we choose CD? We choose CD because here I have said B reaches the region Q earlier than A. B, so that's the part of B, the part of this is the part of the wave. So the wave has got part A and part B. So then we will say number 2, B decreases speed earlier than A. So its speed is going to decrease. Is going to, the wavelength decreases. And then it bends towards the normal. So that is what you will say here. So to get these 4 marks, we can say A, unfortunately, I'm not going to be able to write that B reaches the region Q earlier than A. And then what happens? The wavelength decreases. The wavelength decreases. Then it bends towards the normal. The wave moves towards the normal. Then lastly, the speed of B has decreased. So you are going to get all those 4 marks. Figure 5.2 shows the waves after a change is made to the way the tank is set up and the experiment is repeated. So here, AB, we get CG. The wave from position AP in region P now moves to position CG in region Q. Then, what is the question here? I don't have the question here, but we have to state the change, if any, and explain if there is any change. Let me just look at the question. Anyways, the question is not here, sorry, but we have to state if there is any change. So from the look of this diagram, there is no change. So what explanation can we give? It's just that region P and the depth of region P and the depth of region Q are equal. Thank you.